Hello everyone. For this Sunday, five topics have been released, and the topic which has been noted the most is how code compilation versus interpretation impacts performance. So let's start with the session. The architectures of code execution. So you'll get to know first what a programming language is, right? It's a it's a medium through which we can write instructions to the computer so that the system can execute. So we are actually going to have the code which we are going to write is called as the source code, which we write is dependent on the programming language, depending on the semantics and the syntax of the programming language. So we are going to have source code to the silicon. What it means by silicon is the hardware, because the main component to which we are going to make the hardware for this is the silicon drive. So from source code to silicon, performance, portability, and the translation pipeline. What it means by translation pipeline is that, see, the programming language, the program which you write is in our human level language, which is called as high level language. So this program, this language needs to be converted so that the machine can understand. The machine can only understand zeros and ones, the binary code, which is called as a machine code. So the high level language needs to be converted to the machine level language. For this, we are going to have translators for the programming languages. So these are what which we are going to learn within this session. These translators are, for example, as I have mentioned within the title, interpreter, compiler, JIT compiler, etc. So we are going to learn about these now. So let's go for the next slide. The fundamental gap. Programming languages do not directly run on hardware. Yeah, because the programs which we write through the programming languages are in high level language, human readable language. Execution is entirely defined by how and when translation occurs. So, what it means is that the way the execution happens is dependent on the type of translator which we use. So, you'll get to know about it as we go on with the slides. So, first, let's get to know what actually happens. Like, we have the human readable source code, right? The CPU cannot understand it directly. We need to translate it to machine level code. So for these, we are going to have the translators. So we'll get to know about these translators now. There are three main modes of translations. One is a compilation, interpretation, and the hybrid one, which is the JIT compilation. So what actually is a compilation? A compiler is a compiler converts the high-level language directly into machine code at a time. So the whole program will be converted at a time. So it does not have any pauses. But when it comes to interpretation, it translates each and every line of instruction at one at a time. It's highly flexible, but it's very slow because the lines of the program, the instructions are converted one at a time, right? So it takes a lot of time. JIT compilation. It is going to start translating live. It means that we are going to have an intermediary code when it comes to JIT compilation, which is called as the bytecode. And after this bytecode comes, it will be converted into machine code. So what actually happens is that it is going to remember the common phrases so that it can instantly recall them. So these common phrases can be functions which we use. So modern runtimes balance flexibility, portability, and performance by choosing one or a hybrid of these translation methods. So the type of translator which we use is dependent on the type of problem which you try to solve. Ahead of time compilation. What it means is that we are going to convert the source code into machine code before. So this machine code is platform specific. Platform specific means that, like when we have the devices, there are multiple different types of operating systems, right? Like a Mac will have a Mac OS. When it comes to a Windows laptop, we are going to have the Windows operating system, and we are also going to have different types of Linux distributions. So this is what it means by platform specific. Like for suppose if we run the compiler in Windows, we are going to get the machine code specific to Windows in that way. So what the advantage is, it converts the source code into machine code before execution. So it is extremely fast because the CPU can just read out the machine code and it can perform the execution. But what is the drawback? So, this is a platform specific architecture because the machine code which is generated by AOT compilation is platform specific. So for suppose if we have the executable .exe, a Windows executable, then it cannot run on Linux. We need to recompile it so that we can make it Linux specific, so that it can be runnable on Linux. So it incurs a slow upfront build setup. It means that if we wanted to run in another as architecture, another operating system, then we need to recompile it, right? So that's why it's called incurs a slow upfront build setup. The type of languages which uses AOT compilation are C, C++, Rust, and Go. Runtime interpretation. So when it comes to interpreter, how actually an interpretation happens? We are going to have the source code, the high level code, the human readable code, right? Each and every line, each and every execution unit of that code, of the source code, will be translated one at a time and it will be sent for execution. So it's like a loop where one by one at a time, execution happens. So it's a continuous cycle. Read, translate, execute. Read, translate, execute loop. So what is the advantage of this? Executing code line by line during runtime without pre-compiling enables fast development cycles. And it is portable. Like for suppose if we just have the interpreter within our system, no matter what the type of system is, it can run anywhere because it is not converted to machine code, which is a code which is specific for the type of operating system which we use. So there is the main advantage of interpreter, but drawback is it's extremely slow because each and every unit needs to get executed at a time, right? So it's very slow. The notable languages Python, Ruby, JavaScript historically it means that previously JavaScript also used to use interpreter. Now it uses it compiler. The code trade-off matrix. So let's get to know the main differences between compiler and interpreter. Runtime speed. Compiler is extremely fast because the the source code is directly converted into machine code, right? So the runtime actually happens on the machine code, so it's very fast. Interpreter, it's slow, as you know, because we are going to have each and every instruction executed at a time, so it's very slow. Startup time. Compiler is instant. Interpreter, it's delayed because we are going to have the intermediate steps when it comes to the interpreter, as I have discussed before. Portability, compiler is platform specific because the machine code which is generated by the compiler is dependent on the operating system. But when it comes to the interpreter, it's universal. It can be done on any operating system without having any specifications. Debugging. Compiler is complex because the whole program is compiled at a time. But when it comes to interpreter, it's easier because each and every line of execution of instruction is executed one at a time. So the debugging will be easier. Development speed. The build setup is slower when it comes to a compiler because we are going to because it needs to be converted to machine code pre, right? So the build setup is slower. But when it comes to interpreter, it's rapid as one at a time execution happens. Optimization, compiler has strong upfront, but when it comes to interpreter, their optimization is limited. Takeaway, neither approach is universally superior. Choice depends entirely on system operational requirements. So it's about the type of problem which you are trying to solve. So the type of approach we use is dependent on that. The mechanics of speed, removing overhead. So let's consider where we are going to have 1 billion loop, like we need to have 1 billion iterations. For suppose if we use interpreter at that time, we are going to have 1 billion reads, 1 billion translations, 1 billion executions. So it is going to take a heck load of time. But when it comes to compilation, we are going to have direct 1 billion direct executions because it will be converted to machine code which can be directly executed, right? So the number of operations which are required when it comes to a compilation is very less. So it's extremely faster. Before compiler, so let's get to know about function inlining. Function inlining is where through the compiler action you are going to remove the function call overhead. There are also other different types of compiler optimization techniques like loop unrolling, dead code elimination, the cost of context, memory and startup, compiled binaries. So what compiled binaries means? It is the machine code which comes after the compilation, after the translation of source code to the machine code. So the reason why it is mentioned as it starts instantly because the machine can run it directly without having any other steps. So it's extremely efficient and minimal memory footprint. But when it comes to interpreter, we are going to have the source code, we are going to have a standard library or modules, and we are going to have the interpreter. The RAM usage is very high because these modules need to be taken into the consideration. We are going to have a heavy initialization because of loading the modules, JVM loading classes before a single line of code is run. As it happens each and every time for each and every line of instruction. So the amount of RAM which is used, utilized is also very high because it's not a direct step. We are going to have a lot of intermediary steps. Interpreted runtimes pay a persistent context tax in RAM and boot time just to maintain the capability to execute the code. So what it actually means is that we are going to require to store these lines of execution within the RAM, right? So such that it has the context of what actually is happening within that program. So that's why it is mentioned as persistent context stacks in RAM. Now let's get to know about the hybrid approach, the bytecode. So within the hybrid approach, we are going to have an intermediary step which is called as a bytecode, where the source code is converted into bytecode using a compiler. It's an intermediary portable code. So we know the disadvantage of the compilation, right? So when it comes to AOT compilation, the source code is converted into machine code, and this machine code is platform specific. To rectify this issue, we are going to have an intermediary portable code which can be executed in any type of operating system. So this is the main advantage of the hybrid approach. And on this bytecode, we are going to run the interpreter to convert it to the machine code in whatever operating system which we want to run it on. The compromise systems like Java and C hash refuse the binary code between pure compilation and pure interpretation. The mechanism. Source code is compiled exactly once in an by intermediary state bytecode. A virtual machine then reads this bytecode on any target platform. So because this intermediary code which has been generated can be run on any sort of operating system. The benefit combines the universal portability of interpretation with the structural readiness and error checking of compilation. Just-in-time execution. So what's the difference between the interpreter path and the just-in-time execution? When it comes to the just-in-time execution, the bytecode when the bytecode is being translated by the JET compiler, so it is going to maintain the hot code, the code which needs to be active within the memory, so that It can be accessed instantly. So it's faster when compared to interpreter. So this is the approach which has been created after the hybrid approach. So that as we know, interpreter path is very slow, right? So this JIT compiler path is very faster after the detection of the hot code, even if it's initially slow. So this after the detection of the hot code from the bytecode, it will be optimized into machine code and will be executed by the CPU. The modern engine behind the JVM and JavaScript. So previously we are going to have JavaScript afterwards has started to use JIT compiler from version 8. Adapts to runtime. So what actually JIT compiler is like is that it adapts to the runtime behavior, compiling only the code that matters the most. So what it means is that it is going to compile the code which is active at that particular specific instant. So it can adapt to the runtime behavior. That's what it means. JIT dynamics, the warm-up tags and advanced optimizations. So initially, JIT compiler takes a lot of time because it interprets slowly. It's called as initial warm-up tags, but afterwards it skyrockets and reaches the level of near AOT speeds, AOT compilation. This hot code, so just remember the hot code means the active code at that specific running instance. Advanced runtime optimizations, inline caching, faster repeated operations. What it means is that the repeated operations which are there, which will be cached. Cached in the sense it will be put in the cache memory because right, cache memory is the fastest memory after the registers within the memory ecosystem. Escape analysis, it reduces the heap memory allocations. S- Speculative optimization, assuming common behavior based on live data. Adaptive compilation, continuously re-optimizing our plans. These are the different types of advanced runtime optimizations which we have. The hidden taxes, typing and garbage collection. There are two different types of typings when it comes to programming languages. One is dynamic typing and another is static typing. Dynamic typing means that we are not going to initialize the type of the variable. But when it comes to static typing, we are going to initialize the type of the variable. Like x equal to y, we didn't mention what is the type of that variable, like whether it is a string or whether it is an integer. But when it comes to static typing, we are going to during the initialization itself, we are going to mention the type. Like 5 is an integer, we are mentioning it right away. Int x equal to 5. So this is the main difference between dynamic typing and static typing. Dynamic typing, continuous runtime type checking overhead. But when it comes to static typing, known types allow aggressive upfront compiler optimization. So what it means is that we are going to get to know what type of uh, variable it is instantly when it comes to static typing, right? But when it comes to dynamic typing, that's not the case. It needs to understand during the runtime. The GC pause, what it means is that the garbage collection, like for suppose when the code is getting executed, when garbage collection happens, it pauses the execution such that it finds the inactive variables, inactive code, so it's such that it can remove from the memory. This is called as GC pause. So it pauses the execution each and every time when the garbage collection runs, such that it can remove the unnecessary and inactive code. It makes memory management significantly efficient, but it reduces the speed of the execution because the pauses happens during the code execution. This is useful when we do not require ultra low latency systems. But when we have ultra low latency systems, then having garbage collection is just going to reduce the latency, increase the latency. The Python paradox in AI. So this is a misconception for many people. How Python is being used when the translation medium which Python uses is not compiler, it's interpreter. So how it actually works is that When it comes to Python, we know that artificial intelligence are heavy processing programs, artificial intelligence programs. But the main programming language which is used for AI is Python. How is this working? See, the main reason for it is because Python is just the orchestration layer when it comes to AI. The modules which we have for the artificial intelligence like PyTorch, TensorFlow, and NumPy are developed in C or C++. This is the main reason why Python, even though the AI requires very high processing, the we can use Python for it because the modules which are created are AOT compiled. They are in C or C++, not in Python. Python just acts as the orchestration layer. The secret Python dominates performance critical AI because it doesn't do the math. These computations are not done by the Python. The computations are done by the C or C++ libraries. The libraries are not a Python language. It merely dictates what to compute. So it merely instructs. The mathematical computations are not done by the Python programming language, offloading the execution to compile native binaries. The scale of milliseconds. So, see, even 1 millisecond of execution time saving per request is very high in production systems. Because in production system, it's not just about getting just one request at a time, right? We can get millions or tens of millions of requests. So when we have a lot of volume of requests, it results in enormous financial and computational savings at the scale of billions of requests, at the scale of millions to billions of requests. Scalability. High performance execution handles massively more concurrent users on identical hardware. Infrastructure cost. Faster code execution fundamentally requires fewer provisioned cloud servers. Battery usage. Efficient compiled code drastically extends battery life for mobile and edge devices. User experience. Lower latency systems directly correlates to higher user retention and revenue. The modern execution ecosystem. So let's get a recap. Let's get to know about the applications in here. Let's for AOT compilation, ahead of time compilation. It is mainly useful for game engines, operating systems, core databases. And the programming languages which are used for it are C, C++, Rust, Go. Balance scale, which is going to balance between the having the universal architecture along with the speed. It's useful for enterprise backends, high traffic web APIs, real-time systems. The main programming languages which are used for this is Java, C hash, JavaScript. Maximum flexibility, interpretation. It is mainly used for AI orchestration, automation, and rapid scripting, data science. Python and Ruby are the main programming languages for this. System design is no longer about finding the fastest language. Yeah, this is because that we are going to have various different metrics along with speed. Speed is not just the only metric when it comes to solving real world problems. It is about matching the architectural execution pipeline to the exact constraints of your problem domain. So based on the problem domain, we are going to have the type of translator, the type of programming language which we are going to choose. Thank you.